All right, here we go with 7.5 number 31, which I have a feeling is going to be a beast of a problem, but there's no sense crying about it. Let's just get going. Let's work on it. Okay, so here we go. Um, we've got these two irreducible quadratics in the denominator, and but they're each only repeated once, which is at least silver linings. I mean that's kind of nice. I'm actually going to ignore the integral sign for now and just work with the fraction itself. Okay, so this thing, this factor right here, the x squared plus 1, it has to have a partial fraction of the form ax plus b. Okay, so whatever factor you have, the numerator has to be 1 degree less than that. So if it's a linear factor, if this was just x plus 1, well, 1 degree less than that would just be a constant. So you would just have a over x plus 1. But since it's a quadratic, right, x squared plus 1, the factor in the numerator has to be 1 degree less than that. That would be a linear factor. So ax plus b, right, over x squared plus 1. And then you have to have another linear factor corresponding to the x squared plus 3. So you've got to have a cx plus d over x squared plus 3. Now, some of these things might end up being 0, right? But, nevertheless, this is what we know. The format has to look something like this. If we clear fractions now by multiplying through by that denominator, we get ax plus b times x squared plus 3 plus cx plus d times x squared plus 1. Now, the thing that really is difficult about these irreducible quadratics is that it's not easy to cancel stuff off, right? Like, I can't plug in any, when I plug in something here, when I square it, it's going to become positive. And so then when I add 3, this is never going to get to be 0, right? And so that just makes it difficult. I could let x be 0, and then at least I'll have 3b and d. But that's not going to help me solve for any of those variables. So I think when you run into a situation like this where you're not going to get any low-hanging fruit by letting x be some value, the best thing to do is to just equate coefficients. And the way you equate coefficients is by multiplying this side out, right? So let's do that. So I'm going to have an ax cubed, a bx squared. I like to try to expand these so that they're in descending order. A 3ax, and then a 3b. Okay, and then I'll have a similar pattern over here, a cx cubed, a dx squared, a cx, and a d. So I'm going to collect like terms now. I've got an a and a c, so a plus c x cubed. For my x squareds, I'm going to have a b plus d. For my x's, I'm going to have a 3a and a c. And then for my constants, a 3b and a d. So this actually isn't terrible, I think. But this is where you get your system from, right? We know that a plus c has to equal 1. b plus d has to equal 3. And actually, if you kind of space this out, I don't know, it's sometimes helpful to space it out. Like, if you leave a space for b and d here, but I've already written some stuff down. I mean, it's okay. So b plus d equals 3. 3a plus c. 3a plus c has to equal 1. That's really interesting, right? A plus c equals 1, but also 3a plus c equals 1. and then 3b plus d has to equal 9. This is kind of nice. It's almost like two separate systems, right? Because you could solve for a and c just by looking at these two equations, and you can solve for b and d just by looking at those two equations. So if a plus c has to equal 1 and 3a plus c has to equal 1, well, I could just subtract those two equations, right? Equals 1. So I'm going to subtract these things. A minus 3a is negative 2a. C minus c is 0. 1 minus 1 is 0. So a has to equal 0. Okay, got that. And if a equals 0, well then c has to equal 1, obviously. Okay, that takes care of a and c. Now for b and d, same trick. I'm going to subtract them. Subtract these two equations. So negative 2b, d minus d is 0. 3 minus 9 is negative 6. That means b must be 3. And if that's the case, then d must be 0, right? Okay. Putting it all together then, I think we can go ahead and jump to the integral now. We're going to have ax plus b over x squared plus 1 plus cx plus d. So and that's a piece of cake, right? This is a tangent inverse. This is a natural log. So the rest is history. The partial fractions are definitely the hard part here. Anyway, so that's that. I don't think I'm going to work out 33. Jordan asked about 33 as well. I mean, 33 is actually easier if you look at them, right? 31 was this monstrosity. 33 just has an x squared plus 1, so that's not bad. Oh, actually, maybe I should work out 33. The only thing, actually, I'm not going to work it out. Here's what I'll tell you. The numerator, the degree of the numerator is greater than the degree of the denominator in number 33. So before you even get started on partial fractions, you're going to want to do some long division first, right? So do the long division first, and then you may not even need to do partial fractions, right? But if you do have to do partial fractions, it'll be a lot easier to do once you've done the long division. So just, yeah, that's all you have to watch out for on 33. So do the long division first, and that's that.